How does the relatively low redox potential of the NiFe-PbS material, despite offering an appropriate specific capacity and strong cycling stability as a cathode in aqueous sodium-ion batteries, create a need for further enhancement of its redox characteristics? What are the underlying electrochemical implications of partially replacing iron with copper to synthesize the Cu-Fe-PbS framework, and how does the resulting chemical composition of K.71 Cu, Fe, Cn6, 0.72, 3.7H2O contribute to increasing the average working potential to as high as 1.0 V while still maintaining a specific capacity of 60 mA Hg superscript 1? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? In what way does the introduction of copper influence the rate performance, given that at a high current density of 41.7 C the material's specific capacity is observed to be about 34% of the specific capacity measured at 3C after 500 cycles? And what does this indicate about the trade-off between capacity retention and high-rate cycling? How does the controlled incorporation of copper into the CuxNiPbA's electrode, when cycled in a 1 mol L superscript 1903 aqueous electrolyte, enable the adjustment of the redox potential from 0.6 V to 1.0 V without significantly compromising the reversible specific capacity? How might these modifications and performance characteristics inform further research into optimizing the balance between redox potential, rate performance, and cycle stability in PbAs? And what additional studies are necessary to fully understand the effects of transitional metal substitution on the electrochemical behavior of these promising cathode materials for aqueous sodium-ion batteries? How is the rate performance of the NiFe-PbA material determined when used as a cathode in sodium-ion batteries, and what specific experimental conditions, such as current density and electrolyte composition, contribute to evaluating its high rate charge and discharge characteristics? How does the unique structural configuration of the NiFe-PbA material, including its 3D open framework and ion diffusion channels, facilitate rapid sodium-ion intercalation and deintercalation? And what role does electronic conductivity play in minimizing polarization effects at high C rates? How can the analysis of charge/discharge profiles and capacity retention curves at various current densities provide insight into the intrinsic rate capabilities of the NiFe-PbA material? And what are the key performance indicators that researchers focus on when assessing these properties? How do synthesis methods, such as the self-precipitation process, influence the particle size and crystallinity of the NiFe-PbA, and in turn affect its rate performance and overall electrochemical kinetics?